Let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1203. We started to talk about curve sketching last time. Well, I gave you guys the handout, so let's actually jump into it now. People still trickling in here. Okay. Here we go. All right, so curve sketching. It will cover three sections in the textbook, I think. So this 4.3, 4.4, 4.5. Handout on class webpage. And last time I mentioned, chances are, like on a final, there will be something like here. And everything is like a quiz / test. Okay, all right, so let's actually go through it. So basically the idea is we are going to be sketching curves. Now, on one hand, this isn't really something you would do by hand in general. Most people these days would actually just graph a curve like on a graphing calculator or on a computer or something. But the reason why we tend to keep this guy in a calculus curriculum is that it actually gives a tangible way to make sure that students actually understand some of the more nuanced concepts, you know, like concavity and inflection points and what does it actually mean for a graph? How would it look if a graph has it? Things of that sort. So yeah, by doing this, it's a good way to know that you know what each derivative does and the concepts behind each of the guys that we've been talking about. As well as it puts together a lot of skills. You'll have to remember how to find intercepts. You'll have to remember how to take limits. You'll have to remember how to do the first derivative test, the concavity test, a lot of things. So like several other things we're doing in this class, consists of a 6-step process. You're going to observe or just note the domain of f, write it down. You're going to find the x and y intercepts, as long as that's possible to do that. You're going to find asymptotes, which we spoke about last time, how to find horizontal and vertical asymptotes, which I, again, recopied in the notes here. It's still coming in. We are then going to find the intervals of increase, decreasing, as well as local maximums and minimums. We know that, by the way, for that we can use first derivative test. And the fifth thing we're going to want to do is find the intervals of concavity as well as inflection points. And for that guy, you would use concavity test, which are both tests that I've covered before. So you're gonna have to make sure you remember those. And then finally, you can sketch the graph according to all this data. Some rookie mistakes that students make is things like not knowing what derivative applies to what. So you should remember to find points on the graph, you always use the original function. To find where it's increasing, decreasing maximums or minimums, you use the first derivative. To find where it's concave up or concave down or where there are inflection points, you use the second derivative. So one thing that would cause students to mess up a lot of times is just not knowing. They might use the f prime to find a coordinate or something like that, which they shouldn't be doing. Another thing is just when you find something, make sure that your picture agrees with what you found. Sometimes students will have, they'll work it out and they'll say like, oh, there are 2 x-intercepts or something like that. And then they would draw a graph with 3 x-intercepts or no x-intercepts or something like that. And it's like, well, you told me there were 3. How how come on your picture there aren't, right? So things like that are just the sort of mistakes that I see here often that you really shouldn't make if you just have to pay attention. That being said, we're going to go through several of these examples. I was thinking of going through like 3 of them. So I want to do this one because it's actually a pretty easy one to do. You guys should actually know how to sketch that by heart. And just to show you that the process will actually work, I'll probably also do this one, which is something that technically you could have been able to sketch in, say, a pre-calc course. But now we're going to do it in a lot more detail. You're going to see why things had to curve the way they curved when you're in the pre-calc course. And then I'll do one of these guys. Kind of torn between trying this one. We actually did a graph very similar to that before, or maybe this one. Maybe. So yeah, just want to do this with you guys, and we're always going to go through these 6 steps. So it's another thing like related rates. Know the 6 steps very well, know what order to do them in, and you can do that. Something that does help you out here is usually in the problem itself, I will actually remind you of the things that I want you to find. Consider the given function, find all intercepts, asymptotes, relative extrema, blah, blah, blah. You'll see it there in the question statement. But that being said, let's actually jump into it. Let's see how we are going to do this. So this is the first example. Let me change the size here. So here's the first guy, which it's 1 over x squared. We already know what that looks like. It looks like this, right? Let's see if that we could actually figure out that's what it looks like. If, suppose we didn't know what that looks like, but we do, but let's pretend we didn't know. And let's actually try to graph it. So first thing you're going to do is step 1 is to say you need to pay attention to what the domain is. So that's what we're going to do. Step 1. What is the domain? Well, as long as the denominator is not 0, this is going to be okay. So the domain is going to be everything except 0. All right, cool. That's it. Let's move on. The next thing you're going to want to do is find intercepts. So let's talk about the x-intercepts. Remember, for the x-intercepts, you set y equals 0. So if you set y equals 0, you get 0 is equal to 1 over x squared. You'll realize this has no solution. So this means no y-intercept. We know it has no solution because it's a fraction. A fraction can only be 0 if the numerator is 0, and the numerator here is 1. So it will never be 0. So now you move on to the y-intercept. Y-intercept occurs when we set x equals 0. We can't because not in domain. You would divide by 0. So it also has no x-intercepts. So whatever the graph of this guy looks like, it has no x or y intercepts, which we kind of knew already, but let's pretend we didn't. Now we're just going through and picking up some clues. The third thing we want to do is the asymptotes. Okay. So remember, there were 2 kinds of asymptotes we cared about. We cared about the horizontal ones and the vertical ones. for the horizontal ones, what we do is we find the limit as x approaches infinity of our function, which it's a rational function, so that's actually going to be the same as the limit as x approaches negative infinity of our function. Because it's here, it's a rational function that is not top heavy. Right? These two guys aren't equal in general, but we know for rational functions that are not top heavy, they are. And so we now have to find that limit. What is the limit as x approaches infinity of 1 over x squared?
0.
0. Exactly. Because it's bottom heavy. Now, remember what the rule is. If either of these limits give you a constant, then y equals that constant is the horizontal asymptote. So this means that y equals 0 is a horizontal asymptote. Now we move on to the vertical asymptote. So here we have our f of x equals 1 over x squared. Notice that it's reduced. So this means the VA happen when the denominator equals 0. So this means that x squared equals 0, which means that x equals 0. And so that means x equals 0, that's the equation of a line, is the vertical asymptote. Okay, so just set the denominator equals 0. That was step 3, finding the asymptotes. Step 4 is where we talk about increasing, decreasing, maximums, and minimums. And so we know whenever we're looking for something like that, we're going to use the first derivative test, which means we wanted to use the first derivative. So here we're going to use first derivative test. So this means we're going to find the derivative, right? Which here our f is x to the minus 2. This means our derivative is going to be minus 2x to the minus 3, or minus 2 over x cubed. What you're going to do is you're going to find the critical points. F prime equals 0 or undefined. F prime is never 0. Again, it's a fraction, and the numerator is never going to be 0. The numerator is minus 2. A fraction can only be 0 if the numerator is 0. It is undefined, though, if x equals 0, because you would divide by 0. So that's your only critical point right there. And remember, what we do with that critical point is we put it on a number line that we test in the first derivative. So we're going to put a 0 here. And what we're going to do is we're going to test a random number to the left and to the right. So let's say I can test a minus 1, I can test a positive 1, and we're going to plug it into the first derivative. So the first derivative is minus 2 over x cubed. If I plug in a negative 1 into x, that becomes minus 2 divided by negative 1 cubed. Negative 1 cubed is negative 1, so you get minus 2 divided by minus 1. So this is a positive number. And what does positive mean in the first derivative? First derivative is positive. What does that mean for the function? Remember what we're looking at, increasing, decreasing, max or min. Positive first derivative means what?
Increasing.
It means it's increasing. Okay, so I know the graph is going up as I move from left to right. If I plug in 1 into the first derivative, that's minus 2 divided by 1. That's going to be a negative number. So on this side, it's a negative, which means it's going down as I move from left to right. Now, what does that mean for 0? What is 0 here?
The maximum point.
Okay. So it's not a maximum point. It looks like it is, right? Because you're increasing on the left, decreasing on the right. But it's not a maximum point. Why not?
Because the lines never really touch it.
Because the what?
Can you hear me?
Yes.
The
Yes.
lines never really touch 0.
Okay, what do you mean by that?
All right, I'm not illustrating it correctly. Sorry.
So the lines never touch 0. What does that mean? What's the way you can say that? So normally this would be a max, but it's not a max. Because there's several ways you can say it, because f is not continuous at 0. Or you can say x equals 0 is not in the domain. Right? And that's why step 1, even though it kind of seems silly at this point, oh, you can obviously tell that the domain is that. Why do you need to make that even a step? Isn't that obvious? Well, it's obvious. You do it for this reason. You always want to make sure that you have the guys who are in the domain versus not in the domain in mind. Because if one of those guys become the point at which some feature happens, you need to know that the feature is not going to happen because they're not in the domain, right? So it's increasing on the left, but decreasing on the right, but it's not a maximum because the point x equals 0 isn't on the graph. It doesn't exist. And the way you say that is f is not continuous, or you say it's not in the domain. And so that's why it's not a max. If we were continuous here and we were actually in the domain, it would be a max. But remember the first derivative test, it says if you're increasing on the left, decreasing on the right, and you're continuous at the point, then you are a max, right? A local max. So you have to be careful here. So that's 0 is not anything. All right. So what we get from this section here, section 4, is that we can tell where it's increasing, where it's decreasing, where it hits maximums, and where it hits minimums. Increasing, it's increasing from negative infinity to 0. You can see that right here. Decreasing, it's decreasing from 0 to infinity. You can see that right here. Max, none. Min, none. The only potential candidate for a maximum was 0, but 0 is not in our domain. Now you move on to the next section, section 5. Now in section 5, we look at concavity, concave up, concave down, inflection points. Now we know for that, we use the concavity test. Right? Which means you're going to find the second derivative. Now we know that the first derivative was minus 2x to the minus 3. This means that the second derivative is going to be 6x to the minus 4. Or 6 over x to the 4th. Then what you're going to do is you're going to find the critical points of f prime, which means you set f double prime equal to 0 or undefined. Again, never 0, but it's undefined when x equals 0. So now you plot this the number line, but you test it in the second derivative this time around 0. Plug in a random number to the left and to the right into 6 over x to the 4th. Now 6 is positive and x to the 4th is always positive. So as long as x is not 0, this will always give you a positive result. So it's going to be positive here. Positive in the second derivative means concave up, like a cup. You're shaped like a smiley face. You'll be positive here, which again, concave up, like a cup, shaped like a smiley face. Okay. And yeah, so because we are concave up on both sides of 0, 0 is not an inflection point. But even if we had a switching concavity, it still wouldn't be an inflection point because f is not continuous at 0. So here, not an inflection. Since x equals 0 is not in the domain. Also, we did not switch concavity. So even if it was in the domain, it still wouldn't work. Okay, so 0 again isn't anything because it's not in the domain. Yeah, so what we can conclude from this is, where is it concave up? Where is it concave down? Where are the inflection points? It's concave up almost everywhere, from negative infinity to 0 and from 0 to infinity. It's concave down, nowhere. And inflection points, none. So we have that. Now brings us to step 6. We're finally going to graph it. So essentially what we're going to do now is we're going to take note of all these features we just found, and we are going to put them on the graph. Now I tend to like to do this in a certain order. So let's see how we do that. So here's graph. The Cartesian axes. So here's how I would tend to do it. What the first thing I would do is I would put in all the coordinates that I know I should pass through. So if I found any maximums or minimums in intercepts, inflection points, I would actually plot those points. So I'd say 1, plot the important points. It's like intercepts, max, min, flexions. This one had none. It had none of those here, so we don't really have to plot these. The next thing I would say to do is to put in the asymptotes. Of course, you use broken lines for those, so they're not actually a part of the graph. Remember, the asymptote is just the curve that it heads towards as the x or y coordinate become infinite. So that's the second thing I would put in. We do have that. Y equals 0 was a horizontal asymptote, and x equals 0 was a vertical asymptote. So y equals 0 is just the guy running along the x-axis. X equals 0 is the guy running along the y-axis. So I put those guys in. The next thing I would do is I would put in the intervals of increasing, decreasing. How would I do that here? Well, I would do it like at the bottom of my graph, just to kind of dissect the area that I want to do it on. I know it's increasing from negative infinity to 0, and it is decreasing from 0 to infinity. So I can put that in here. So I can say from 0 all the way back, I know it's increasing. And from 0 all the way forward, I know it's increasing. So again, the increasing isn't a part of the graph. That's just me just kind of blocking out the interval that I know I wanted. So that's that. Then I would put in the intervals of concavity. Okay. Which again, it's from 0 to infinity, negative infinity to 0 and 0 to infinity, but we were concave up both times. And now once you actually have that, you have everything that you'll need to draw the graph. You can literally forget about everything we wrote before. Everything that you now need to draw the picture is on the picture so far. So now you want to start to draw a curve. You can start by plotting points if you want. So for example, if you were to plot the point 1, you know, you'll get the point 1. Just to kind of test where the graph is in each region. In this case, though, there are ways that we could know that it would not. Sorry, did I put this should be decreasing, but increasing both times. Should be decreasing. For this particular graph, there are ways, and with many of the other graphs, there are ways that we can know what would be the answer versus not in the answer. Okay, so for example, could my graph be down here? The answer is no, because it's supposed to be decreasing this whole time, and I know it's supposed to hit a vertical asymptote. If my graph was down here, it would necessarily create an x-intercept, which I know there is no x-intercept. So I know, even without testing a point, that it cannot be below the x-axis here, because it cannot be below the x-axis and be decreasing. It would create an intercept. So I know my graph is not there. It has to be on top. For similar reasons, I know my graph cannot be down here, because if it's down there and it's increasing, it's moving as I go from left to right, and it's going to hit a vertical asymptote when it hits the y-axis, it means it would have to do this. But in order to do that, again, it would create an x-intercept. So I know it doesn't have an x-intercept, so the graph could not be below there either. The graph must be also above here. The graph must be on top the whole time. That being said, now I would know what the graph would look like, because it would have to look like this. Right? It has to approach the y-axis as it's moving to that way, has to approach the x-axis as it's moving that way, and it's concave up like a cup. Notice that it's shaped like a smiley face. Similarly, the other side would be like that, which it's kind of supposed to be symmetric, but you get what I'm trying to say. Remember this one. Right? And that's the graph that we know and love, 1 over x squared, right? So of course, I do realize it seems like we went through a lot of trouble just to get that. And to be honest, the questions on curve sketching are going to be among, I'm pretty sure it's the longest. Curve sketching is going to be the longest problem type that you do in this course, for sure, right? So you're going to spend a long time on this either way. But the reason why it's worth it is because if I didn't know this by heart, I could actually figure it out. So the fifth thing you would do is graph here. And that's the order in which you do the graph. Now, I illustrated with this guy because it was familiar. You know what the answer should look like. So hopefully that kind of convinces you that when we go through and test all the numbers, these things actually work out. Let's try another example. Okay, let's do it for this one. Okay. And on one hand, this one shouldn't be too bad. It's x to the fourth minus 4x cubed. But let's actually do it. So we're going to quickly go through and do all 6 steps that I just did, right? We try to do it a little quicker so we can get through another example. So 1, find the domain. Domain is all real numbers here. It's a polynomial. Okay, cool. 2, we're going to find the intercepts. So first you go in for the x-intercept. You know, you set y equals 0. This implies your x to the fourth minus 4x cubed equals 0. We know how to solve that. Factor out a common x cubed, you get x minus 4. So you get x equals 0 or x equals 4. And these guys here are your x-intercepts. Y-intercepts, you know, you said x equals 0. This would mean that your y equals 0 to the fourth minus 4 times 0 cubed equals 0. And so that means y equals 0 is your y-intercept. Those are intercepts. The third thing we want to do is find the asymptotes. So third thing, we're going to find the asymptotes. Horizontal asymptote, none, right? It's polynomial. We spoke about that last time. It's a non-horizontal polynomial. Sorry about this. My headphone's connected to my phone. Someone's calling me. Let me disconnect this thing. Vertical asymptotes, again, none. It's a polynomial. Moving on, 4. We're going to do increasing, decreasing, maximum, minimum. We're going to use the first derivative test. We're going to find the first derivative. Of x to the fourth minus 4x cubed. So that's going to be 4x cubed minus 12x squared. Now you're going to find the critical points. This means 4x cubed minus 12x squared equals 0 or undefined. It's never undefined. It's a polynomial. So this is a guy we want to find. Common term is 4x squared. I'd be left with x minus 3. So you get that x equals 0 and x equals 3 are your critical points. Now what you're going to do is going to plot those on the first derivative. Let's put 0 here, 3 here. Going to pick random numbers in between. And I'm going to plug them into the first derivative. Plug blue numbers into here. It's normally nicer to plug it in the factored form because remember, you don't actually care about the value. You more care about the sign, whether it's positive or negative. And it's going to be easy to see that in the factored value because you can just take positive times negative and positive times negatives. Here, 4x squared is always going to be positive once your x is not 0. So we only need to know about the sign of x equals minus 3. If I plug in minus 1 into x equals minus 3, I get a negative number. So over here, it's negative. If I plug in a positive 1 into x equals minus 3, I get a negative number still. So that's negative. If I plug in a 4 into that, I get a positive number. So that's positive. So here I am decreasing, decreasing, increasing. Now, notice that 3, this has to be a maximum. Why is it a minimum? Sorry. Why is it a minimum? I'm decreasing on the left, increasing on the right, and my function is continuous at 3. So I actually literally pass through the point. So I'm decreasing and I pass through the point and then I start increasing. That means I just hit a minimum. Now to find where that minimum is, I would use F to find the coordinate. When I want the location, I use the original function. So this means that the y value equals f of 3. And I go and I plug that in. So that's 3 to the 4th minus 4 times 3 cubed. I can take out a 3 cubed. It's 1 minus 4. So that's going to be minus 27. 3 minus 4, which gives you a minus 27. Now, so this means ultimately I can talk about where I'm increasing, where I'm decreasing, where I hit a max, where I hit a min. I hit a min at 3 comma minus 27. Where am I increasing? From 3 to infinity. Where am I decreasing? From negative infinity to 0. And from 0 to 3. Where do I have a max? Nowhere, none. So that's this. Moving on to the next section, section 5. Here we're going to figure out concave up, concave down, inflection points. For that, we need the second derivative. Now, the first derivative was 4x cubed minus 12x squared. So the second derivative is going to be the derivative of that. So that's going to be 12x squared minus 24x. And you're going to find the critical points. I'm going to set this guy equals 0 or undefined. It's a polynomial, it's never undefined. Here, common term is 12x. I would get x minus 2. So I get x equals 0 or x equals 2 are my critical points. This time I'm going to plug them in the second derivative. And you plug in random numbers in between. So like a -1, a +1, and a 3, say. I'm going to plug those guys into here. Now, if I plug in a -1, I get a negative times a negative. That gives me positive. If I plug in a 1, I would get a positive times a negative. That gives me a negative. If I plug in a 3, I would get a positive times a positive. That gives me a positive. So here I'm concave up. Here I'm concave down. And here I'm concave up again. Now, what that means is this function is continuous everywhere. So it's continuous at 0 and at 2. So we do actually pass through the coordinates when x is 0 and 2. You would also know that I switch concavity. At 0, I'm positive concave up on the left, concave down on the right. So this guy is an inflection. Similarly, for 2, I was concave down on the left, concave up on the right. So I switch concavity. This is also an inflection. Now, what is the coordinates? So the y coordinate is going to be f of 0, which is 0. So that's 0, 0. And for this one, the y coordinate is going to be f of 2, which is going to be 2 to the 4th minus, what is it, 4x squared times 4 times 2 squared. And that would be 2 to the 4th minus 2 to the 4th. That looks like 0. So here it happens at 2, 0. So now we can summarize this. Where are we concave up? Where are we concave down? Where do we have inflection points? Concave up on negative infinity to 0 and 2 to infinity. We're concave down on the interval 0, 2. And we have an inflection points at 0, 0 and 2, 0. So now remember, these are intervals. And this one, these are points. That was step 5. And this brings us to 6, where we're going to graph. Now remember how we do that. This is going to be mostly to the right, based on where we have the intercepts were 0 and the x-intercepts are 0 and 4, and then I have maximums at 0 and 3, inflection points 0 and 2. It looks like it's going to be mostly to the right. So let's kind of keep that kind of skewed to the right there. Okay, so now we're going to put in the features. What do we put in? The coordinates first. What are the coordinates? Well, my x-intercept is 0 and 4. My y-intercept is 0. So this is an intercept. And this is an intercept. All right, what other coordinates do we have? We have a minimum at 3, negative 27. So at 3, let's just make this random number negative 27, I have a minimum. All right, what other coordinates do I have? I have 2 inflection points. 0 is an inflection point. And then 2 sorry, this was cubed. Yeah, that didn't make any sense. 2x cubed, which that would be 8 times 2 minus 4, which is minus 16. So we're going to have an inflection point at 2, comma, say, minus 16. So those are all my coordinates. Now let's put in, the asymptotes aren't there, so let's put in the intervals. 0, 0 to 3, and 3 onwards. So we have something going on up to 0, something between 0 and 3, and something from 3 onwards. Over here, we're increasing, while over these other 2, we're decreasing. What else do we need to put in? Inflection points, the concavities. 0, between 0 and 2, and then 2 to infinity. So there's one that goes from 0 back, between 0 and 2, and then from 2 to infinity. And it was concave up on the ends, concave down in the middle. Yeah, and that is now everyone. All the information that I had above is now on this picture. So I know all the coordinates I need to pass through, and I know what I need to look like when I'm passing through them. Notice that on the far left, when we're far left of 0, we're decreasing concave up, which means we're decreasing, but we're shaped like a smiley face. So we're doing that. Now at 0, we pass through an inflection point. So we move from concave up to concave down. So between 0 and 2, I'm going to shape like a frowny face. So I need to look like this. Right? So it goes like that. Right? Then from 2 onwards, I'm concave up. So I'm shaped like a smiley face for the rest of the graph now. However, I'm still in the decreasing section, as you can see. So I'm still decreasing, but now I have to shape like a smiley face until I hit the minimum, at which point I start going higher like that. So it's kind of like a little wavy thing. It's like that. But now you see how it had to curve, what you had to do. So you have these points here, and that's a picture of the graph. Okay. This took longer than I expected. So what we're going to do is I'm going to leave the last one. Now this one is going to be somewhat challenging. Probably more challenging than the ones that we've done to this point. But the nice thing is when I give you these challenging ones, I'll actually give you the derivative along with it. So you'll notice here that I gave you the first derivative and the second derivative. So when you're doing a problem like this, I would have already asked you about derivatives earlier in the test. So I'm not going to test you on derivatives again here. I'm going to assume you know how to find them. And so I'll just give them to you here. So what I would say is try this for next time. It will make next lesson go smoother, but it'll also give you good prep for the second test and the final. So what I would say is try this for next time. Okay. If you can get through that easy, I don't think you have to worry about the curve sketching problem for test 2 and the final. On average, what you should be aiming for, aim for 10 to 15 minutes on these. You don't really want to take longer than 15. I think on average, it'll take the average student, once you practice enough, it'll take you 10, 12 minutes, maybe 15 to do this. But if you want to make sure that you can do this, the kind of time that I'm having in my head that I would be assuming you can do it within, it's like around 15 minutes. So you do that. If you take longer than 15 minutes, you can just try the others as well. There are 2 more of that type. Try to do those in less than 15 minutes. And you can easily like plot these by going into Wolfram Alpha or graph.tk, type these functions in, and you can check your own work. But next time we'll do A. So next time we'll do the second example part A, and we'll move on to another topic, optimization, another word problem, but we will try to get through it nicely. So yeah, I would do that, do this example for next time, and yeah, we'll stop there. Thank you for your time and attention. I will see you guys on Friday. So yeah, all right, I'll see you guys in the next one. Ciao.